Okay, hello and welcome back. This video will cover 6.6, which is on the phase shift. So we've been spending some time looking at the graphs of the six trigonometric functions and various modifications and movements and shifts of these functions. And we saw with the trig functions, some familiar graphing transformations have kind of like alternative wave-based names. So just to bring a couple of those up, we saw a vertical stretch or compression that was associated with the amplitude of a wave. A horizontal stretch or compression affected what we're calling the period of the trig function. A vertical shift didn't really have a special name, but you could see that as affecting the sinusoidal axis, like the axis in which, say, a sine or cosine wave is fluctuating around. That will shift the location of that either up or down. But something we haven't discussed yet is a horizontal shift, a horizontal movement. And this is what we're going to call a phase shift. Because in terms of waves, if we take a kind of like a physics perspective, um, it's often described as the phase of the wave. And this determines where the starting point of the wave begins. You can imagine it that way. Even though it does continue infinitely, we can imagine some particular initial value. We can shift that to the left or right. So let's see how this will show up in a few different examples. And this graph or this little chart brings up those terms again: the amplitude, the period, and now what we're going to call the phase shift of a wave. So they use this like omega and the Greek symbols. I tend to just use like A, B, C, and D. So I'll write out how I tend to view these, but you're welcome to use any particular symbols that you would like. So you could have something multiplied in front, um, something multiplied inside, and I'm going to write it in here in this factored form. So I can say b times x minus c in parentheses plus d. We could also have a similar thing for the cosine. So I'm writing this in factored form because you end up having to do this operation of separating out the thing that's affecting the period from the phase shift. And we see that here by this division in their notation. So let me just label what I have here. And this kind of sums up our properties. So we can say the amplitude of either of these waves is the absolute value of A. Just take the positive value. If it's negative, that implies that we're doing a reflection across the x-axis. The period, we take the base period of 2 pi and then divide by whatever that b term is inside. And then if it's factored out like this, if we have our thing that's being added or subtracted from x in parentheses inside, then we can read directly this value c as the phase shift. We can say we have a phase shift of this value c, and that's a horizontal shift. And keep in mind, with horizontal movements, it's kind of backwards in logic. If you remember horizontal shifts, say with x squared, if we had x squared or x minus 2 squared, x squared is centered at the origin. If it's a minus in here, it ends up moving it to the right. So this would move it over to positive 2 here. So a little bit backwards in thinking. If it was x plus 2, then it would shift it 2 spaces to the left. So just keep that in mind, and we'll see some examples of this, but it has that same kind of peculiarity of a horizontal shift. And then we can say the vertical shift will be whatever this d value is. And if that's positive, then it shifts upwards. If it's negative, it shifts downwards. Okay, but for this to be true, this statement, for it to be exactly equal to what is added or subtracted from our x term, it needs to be in this factored form. I'll just say in factored form. But then we also have the tangent and cotangent. We have a times the tangent of b times x minus c plus d, or the cotangent. We can come up with similar statements. Remember the the tangent doesn't, we don't describe it as having a period, so I would just call this vertical stretch. So that would be our a term. For the period of the tangent and cotangent, still follow this pattern of taking the base period and then dividing it by b, but the base period of the tangent and cotangent is just pi instead of 2 pi. So we take pi and divide it by b. And then the phase shift will be the c value, and then we can have a vertical stretch. Or a vertical shift, I mean. We already covered stretch. And that's the phase, or no, vertical shift is this value d on the outside, up or down. Phase shift is c, and again, it's in this factored form. So let's see a couple examples. So we're given y equals 3 times the sine of 2x minus pi. And so this time we definitely have some kind of a phase shift. But first I'm going to factor that 2 out inside of the sine. I'm going to write this as y equals 3 times the sine of 2 times x minus, now what should this be? If I'm factoring out 2, there's not a 2 there, but we can be a little bit tricky and write this as pi over 2. That's essentially what we're doing. We're dividing by 2 when we factor something out, or dividing by whatever that factor is. And you can always test yourself, try multiplying this back in. 2 times x is 2x, 2 times pi over 2, or negative pi over 2 is pi. It would cancel with that 2. So you can always factor something out and just kind of change what's inside, turn it into a fraction. So a little trick there. So from here we can read all of our properties. This is a sine wave that has an amplitude of 3. We can get the period by taking 2 pi and dividing it by the number in front here, which is 2. 2 pi divided by 2 is pi. So the wave will happen twice as fast. And then now we can see our phase shift as being pi over 2. And since there's a minus, it's going to move it to the right. So pi over 2 to the right. So we've been graphing with amplitude changes and period changes, just not yet with a phase shift. So first, let's try to get the graph of something a little bit simpler. Let's say 3 times the sine of 2x. So let's try to do 2 and 1 this time. We've been first doing the change in amplitude, then the change in the period. But I think we can do 2 and 1, because if we know the new period will be pi, it's still going to follow that pattern of the sine, where it goes through 4, really like 5 key points. So even without labeling our axis, we can still follow the general pattern of the sine, because we haven't shifted it to the left or right yet. So it'll start at the middle, go up to the top, down to the middle, down to its minimum, back up to the middle point. We just need to choose how we're going to label these axes. Well, I know it has an amplitude of 3, so I'm just going to call this positive 3, negative 3. We can add a few extra notches if we'd like to. And then since I know my period is pi, this should go out a distance of pi where it completes this whole sinusoidal curve. I should have filled in my curve earlier too. So that means this must be going out to pi over here. Well, and half of that is pi over 2, and half of that is pi over 4. So that would make this 3 pi over 4. So a lot of it is really just about how we're labeling our axes in order to get these graphs. So this would be the point pi over 4, 3. This would be the point 3 pi over 4, negative 3. And we have some points in the middle. So kind of an easy way to get a couple transformations at once. It's still going to follow that sine wave pattern, but the axes are scaled differently because we have various shifts in the vertical direction or shifts in the horizontal direction. Or I should say stretches. Stretches or compressions. So now let's introduce a phase shift. So this will be a horizontal shift of pi over 2 units to the right. So for a phase shift, I always imagine thinking like, where's my starting point going to go? If at 0, it's going to shift pi over 2 units to the right, I'm going to think about the wave starting over here at pi over 2 and then going through that sinusoidal curve pattern. So first I'll label, we're going to do the whole thing, y equals 3 times the sine of 2 times x minus pi over 2. So let's see, let's make it a little bit longer because I'm shifting to the right. So this would be positive 3 let's make this negative 3 down here. So let's see. We're counting in units of pi over 4 for this particular graph. So this would be 1 pi over 4, 2 pi over 4, this is pi over 2. So that's where our first point should be, since we've shifted over to begin there, so the equivalent of this point. Then I really just want to go like 1, 2, 3, like 4 more 4 more points out from here, or 4 more little notches on the x-axis. This would be 1 pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, which is right as 3 pi over 4. Then 4 pi over 4 is pi, and we would have 5 pi over 4, and then 6 pi over 4, which that would reduce to 3 pi over 2. We can probably stop there. So starting at pi over 2 now, instead of starting at 0, so we went over 2 units. Now I just need to follow that sine wave pattern. So it'll go up to its maximum up here, back down to its minimum, or back down to the middle point, I mean, then down to its minimum, then back up to the middle point. We can imagine connecting this with a smooth curve. And then the wave will continue. So it's not like it's not existing over here. Um, but we just moved the period that we're looking at over with the horizontal shift. So we just picked this graph up and just scooted it over by pi over 2, like 2 clicks basically, because we're in sections of pi over 4. So let's label a few of these points. This would be, instead of 0, 0. Now we can imagine adding pi over 2 to all of the x values. So this will be, so this was 0, 0 here. This will be pi over 2, comma 0. And then this will be over here at 3 pi over 4, positive 3. You can also get that by adding pi over 2 to pi over 4. Then we'll have the point pi 0 instead of pi over 2, 0, adding pi over 2. Then this will be 5 pi over 4, negative 3, and then 3 pi over 2, 0. So just adding this possibility of a horizontal shift to our collection of modifications to these trig graphs. So I kind of introduced a couple ways to think about this. Either just pick your starting point from your previous graph before the shift has occurred, and then find out where that's going to land, and then you can just continue the sine wave pattern after that on your graph. Or another way to get the exact location of your points is to just take the previous x values and then add or subtract the horizontal shift. In this case, we were going to the right, so we added pi over 2 to every point, to the x values at least. So whichever way feels better to use, you can use kind of a combination of two. It's good to check that you're landing in the right points. But in my mind, I think about where should the wave start, and then just follow the wave pattern from there. And if this was a plus pi over 2, then everything would be shifted over to the left. It would start at negative pi over 2 instead of starting at 0. So I think we see a left shift for our next example. So let's see. We have y equals 2 times the cosine of 4x plus 3 pi plus 1. So we're kind of combining everything together. I think there's every possible movement. Maybe not a reflection on this one. That would be, we wanted to really make it all in one. But first, let's factor that 4 out inside. Let's put this into the factored form. So I'll say y equals 2 times the cosine of 4 times, and what would be left over? We'll have just the x. And then just like before, we can just place our previous term here and have it being divided by whatever term we're factoring out. So I can write this as 3 pi over 4. Takes a second to get used to that trick, but it's actually extremely handy. And just if you're ever doubting, did you do it correctly, just multiply it back through and see if you get the previous statement back. That would give me 4x. Okay, so that works out. And then 4 times 3 pi over 4. Well, the 4's would cancel. I would just get 3 pi. So you get your previous term. So you can double check. That's always a easy spot to check your work. And then we still have the plus 1 out here too. It's easy to forget that on the side as well. So good to double check. Okay, so let's write out what has happened to this graph. The original graph is the cosine. And let's see, the amplitude is 2. We have our 2 out in front. The period will be the base period of the cosine, which is 2 pi, divided by the number that appears out in front here. So 2 pi divided by 4 will reduce to pi over 2. So the wave is happening 4 times as fast as the original cosine wave. And then our phase shift, now that it's factored out, we can read it straight from the equation. This will be a distance of 3 pi over 4. And since there's a plus here, that means it's going to go to the left. And then we also have our plus 1 on the outside. So this is going to be a vertical shift up 1 unit. So a lot's happening to this graph. But we've been doing lots of amplitude changes. We've thought about changes in the period. The vertical shift will just cause us to shift everything up 1 unit. But let's first produce a graph, maybe just of the amplitude and period change. So let's say we're doing y equals 2 times the cosine of just 4x. And then we'll introduce the vertical and horizontal shifts after that. And so just like before, I know it's going to follow the basic cosine wave, which means it's going to be divided into 4 sections. It'll have some amplitude. The cosine begins at its maximum, then goes down to the middle, then down to the minimum, back up to the middle, and then back up to the maximum. The general pattern of the cosine wave. And now I know the amplitude is 2, so I just need to label this axis as positive 2 and then negative 2 down here. There's like 1 unit in between. And we said the period was pi over 2. So that means this whole wave will happen in a distance from 0 to pi over 2. Well, half of pi over 2 is pi over 4. And then half of that, if we multiply that by 1/2, that would make this first little notch on the x-axis pi over 8. So we're counting in pi over 8. 1 pi over 8, 2 pi over 8. This would be 3 pi over 8 for the third point, and then 4 pi over 8, which reduces to pi over 2. That'll be 1 full period. Another way to think about this, I'm just trying to present like multiple ways to get little tricks for this. If we know originally we went out to 2 pi, and we had pi, pi over 2, and so on, and we're dividing everything by 4, which is what happened to the period, you can just go here and divide all of these by 4 and then reduce the fraction. So pi over 2 divided by 4, you end up with a 4 multiplying in the denominator. That'll give you your pi over 8, pi over 4, and pi over 2 over here, with 3 pi over 8 in between. So just showing some different ways to quickly get the period kind of spacing when we're drawing a graph by hand. Okay, so this is 2 times the cosine of 4x, but let's now add the vertical shift up. I'll just draw the graph right next to it here. So 2 times the cosine of 4x plus 1. We'll just take our previous graph and shift everything up 1 unit. So it's helpful to think where that middle axis is going to go. On the original graph, it's going through the origin at 0, but it's going to be shifted up 1 unit. So I can imagine like an imaginary line going through here. That's like our new x-axis in a way. It's the line in which the wave will be fluctuating around. Or our middle point, we can view it as it's going to be hitting that imaginary vertical line, or horizontal line, I should say. Okay, so everything from the previous graph has been shifted up 1 unit. So instead of hitting positive 2 here, it should go up to 3. So that's where our maximums will be. And instead of down here at negative 2, it'll just go down to negative 1. That's where the minimum points will be. And then let's just put in our cosine pattern. So starting at the maximum, oh, and let's label the x-axis too. So we want to go out to pi over 2. This would be pi over 4 in between, and pi over 8, and 3 pi over 8. So the cosine starts at the maximum, then goes to the middle point, down to its minimum, so it'll be down here at negative 1. Then back up to the middle point, and then ending, not really ending, but ending the wave pattern back at its maximum. So something like this, where we would have the point 0, positive 3. This is up here at positive 3. And a minimum point at pi over 4, negative 1. And so on. We could label the others as well. So we want to get this horizontal shift, this time to the left. We want to get our full graph of 2 times the cosine of 4 times x plus 3 pi over 4 plus 1. So we're getting in this horizontal shift now to the left by 3 pi over 4. So we can imagine adding 3 pi over 4 to all of our previous x coordinates. Or I'm sorry, subtracting, because we're going to the left this time. You can imagine subtracting 3 pi over 4 from all of our x coordinates. So I'll still consider where this wave will start. I'm thinking about where this initial point, this point 0, 3, is going to begin, and then it will follow that cosine wave pattern afterwards. So if I'm going to the left by 3 pi over 4, it should just begin at negative 3 pi over 4. So I'll consider starting my graph there. Something like this. So it'll be somewhere over here. I'll just call this negative 3 pi over 4. And then each distance is in pi over 8ths. So it'd be a little bit tricky. But let's say this is minus 1 pi over 4. So this would be roughly minus 2 pi over 4. And the pi over 8ths will be in between. So the first one would be minus 1 pi over 8. That's half of pi over 4. So each unit is 1 pi over 8. Minus 1 pi over 8, minus 2 pi over 8, which is minus pi over 4. 3 pi over 8, minus 4 pi over 8, which reduces to minus 2 pi over 4, and so on from there. That's kind of the tricky part. But once you get your subdivisions of the x-axis down, then you can just follow the regular cosine pattern. So we said earlier we want to go up to positive 3. And that central axis was at 1. Let me make this look a little bit nicer. So somewhere here. And again, this isn't an asymptote, but I'm just trying to visualize that central line. So then the cosine wave will start at the maximum point. So up here, at negative 3 pi over 4, positive 3. Then it will go down to the middle point. Then we said its minimum point was down at negative 1. So down to the minimum, back up to the middle point, and then it will end in the maximum point. So our curve will look something like this. And then continue on from there. This wave does repeat infinitely in both directions, but we can see one period of the graph, how it's been shifted over to the left. So instead of starting at 0, it now starts at negative 3 pi over 4. So let's label a few more points. That was our peak point here. This would be, how many pi over 8s out are we? 1, 2, 3, 4, 5. So negative 5 pi over 8, positive 1. Then we have negative 2 pi over 4, negative 1. And this would be negative 3 pi over 8, positive 1, because we're 1, 2, 3 pi over 8s out. And then the last point in the cycle, in the period, would be here at negative pi over 4, positive 3. So this one's probably the most tricky one we've seen so far. It involved pretty much all of our modifications except for a reflection across either axis, so we saved that one. But we had both an amplitude change, a vertical shift, a phase shift, and a change in the period. So I did it again in a couple steps. It helps me to go and increment something a bit simpler that I can graph, and then I add the last couple transformations. And then I start thinking about where the wave will begin and find that first point, and then follow the cosine or sine wave pattern from there. But we could have also found the coordinate points here, all of our x coordinate points, and just subtract 3 pi over 4 from each of them, and then that will tell us specifically where each of those points will go. And then if you are, say, like working on a digital homework where you're having to select from multiple choice graphs, like select which one is your graph, it's helpful to think about that starting point idea as well, because likely they might show like the full continuing wave. So you'll need to and try to identify a starting point of the wave, like the cosine starts at a maximum point. And that can help you get an idea of how the graph has been shifted to the left or to the right, whereas the sine wave starts at the middle point. And really, the sine and cosine waves are just shifted versions of each other. You could equally describe something as a cosine or some shifted sine wave. And that's another area where the co-function relationship between the sine and cosine come back into play. That they describe aspects of complementary angles. Um, so you see a lot of shared properties between those two. All right, and I think the textbook gives you a nice summary diagram for graphing functions that have all of the transformations in there. So let's see their suggestion. They say step one to find the amplitude and the period and find out what the phase shift is. And they use this other formula. Basically, that's showing the factoring out of the term that's in front of the x. They're calling it omega here. And this is the term that appears inside. So the phase shift would be that value divided by this value that was factored out. So same idea there. So that's what we did. We started off first by just listing out our properties. What's the original function? What's the amplitude, period, and the phase shift? And it looks like they use the same starting point idea. Determine the starting point of one cycle of the graph. And you can determine the ending point too. So that would tell you where to start and where to stop. Yeah, we shifted the first point over, and we can imagine where that last point shifts over to as well. After that, they divide the interval, so the interval between your starting and ending point, into 4 sub-intervals. So we did that same kind of idea, because we know that the cosine and the sine wave go in those 4 interval patterns. Then it says use the endpoints of the sub-intervals to find the 5 key points on the graph. That's those maximum, middle, and minimum points. So the order will depend on if it's the sine or cosine wave. And then to plot the points, and then it says if there is a vertical shift to apply the vertical shift. So we followed a similar kind of style. We actually did the vertical shift before we applied the phase shift, but you can do them in whichever particular order you would like to. I always tend to save the horizontal shift for last because that ends up being one that's slightly tricky. I like to have all of the other points sort of in order before making that last move. All right, that's all we will cover in this section. So this was the phase shift section 6.6. We looked at graphing sinusoidal functions of these form. So we got the full combination of transformations. Okay, that's it for this video, and I'll see you next time.